Hi everyone, welcome to our second lecture. This is a lecture on 1D kinematics, and it's for the calc only students. Okay, so what is 1D kinematics? Well, the word kinematics in physics refers to a mathematical description of the motion. Okay, so it doesn't attempt to give an explanation for why things move the way they do, but just says, how would I, there's some motion there that we see experimentally. How would we convert that motion that we see experimentally into something which is numerical? Okay, so that we can do analysis on it. And so that's what the word kinematics means, just a mathematical description of the motion. The 1D means that it's along a straight line. Okay, so we're going to begin simple along a straight line. Later on, we're going to do 2D kinematics, which involves vectors and therefore more complicated math. So that's why we start off with the 1D. We won't do 3D kinematics because once you've done 2D kinematics, extending it to 3D is not that difficult. All right, so how would you do that? How would you begin to give a mathematical description of the motion? Well, I don't have an experiment for you here, so we're going to have to imagine an experiment that we would do. And you can see here in my diagram, I want to give the mathematical description of a car driving down the street. So this poor diagram here, poor picture of a car, this triangle, that's supposed to be a car which is driving down the street. And I want to convert that, say we take a movie, and I want to convert that into a mathematical formula. So how do you begin doing that? Well, the first thing is you've got to have some kind of measurements going on. And it's kind of obvious that if you want to know where the car is, you're going to be measuring distances, and that's a length measurement. So you're going to need a ruler. Okay, so down here along the bottom, you see this x-axis. It is an x-axis, but you can think of it as a ruler. We simply place this ruler down along the road, and we fix it there, and then as the car drives by, at any given instance, we can say where the car is on by reading it off the ruler. One of the important things in doing this is that you have to have a reference point. Every ruler has a 0, okay, and so you simply choose some particular reference point. And here I have this diagram of a tree here, and I've simply affixed the 0 of the ruler to where the tree is, and that's my reference point. We call that the origin. Okay, so when the car is actually at the origin there, we would say that it's at position x equals 0. All right. A minor thing, you're actually going to do this in the lab. A minor but important thing is, the car itself has some extension. So you might say, well, how would I measure? Do I measure to the back of the car? Do I measure to the front of the car? It doesn't matter as long as you're consistent. And you'll be doing this in the lab actually with linear air track. So instead of a ruler here, you're going to have a linear air track with a ruler attached to it. And you're going to have a glider on top of the linear air track, which moves back and forth, just like the car here. Okay, so you could simply say, you know what, we're just going to measure from the back of the car. Okay, so you pick one side of the glider on the linear air track, and you say we're just going to measure there. All right, so there you go, you have that. And you need one other thing. You need a watch or a clock of some kind, like a stopwatch. And the reason you need that is because the car isn't just going to stay in one place. Well, it might if it's trivial motion, but if it's actually moving, it's going to be at one place at one time, and another place at another time, and another place at another time. And so you have a clock here. I haven't drawn the clock, but you can see on top of my diagrams of a car, I have t equals 0 seconds. Okay, so that's what this says, t equals 0 seconds. So that's where the car is at t equals 0 seconds. So if I look at my stopwatch and I say, oh, it's at 0 seconds, it's right there. Okay, and then tick, 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 tick. At 1 second, the car might be over here, and so on and so forth. Okay, so you could see that this experiment shows the car at particular positions, that is values of x, at particular times. Okay, so what you can do is you could start to just start, saying, asking the question, where's the car at t equals 0? Write that down. Okay, where's the car at t equals 1 second? Write that down. Where's the car at t equals 2 seconds? Write that down. And then construct a table. Okay, and so here's the example of a table. And I've got time on the left column here. Okay, and I've got the position x in the right column here. Okay, so the left column and the right column. And at 0 seconds, the car is at, say, 1.6 meters. At 1 second, the car is at 3.0 meters. At 2 seconds, it's 4.0 meters. At 3 seconds, it's at 3.0. At 4, it's at 1 meter, like that. Okay, and so you can actually see, that it actually stopped and turned around and came back because the distance from the tree is actually decreasing. So, here the distance to the tree is increasing, then it gets like 4 meters at 2 seconds, but it actually decreases. So it's as if the car stopped and started to go backwards. All right. The first thing you'll notice about this table is that, yeah, it is a description of the motion. And it's kind of what you would get experimentally. And in the lab, you will get a table like that. It'll actually be produced by a computer that'll actually take sort of these snapshots of the linear air track, of the glider along the linear air track at given instances of time. Okay. But it isn't a complete description of the motion because you can actually ask, where is the car at half a second? Where is the car at 1.5 seconds? Where is the car at 2.5 seconds? Okay. I mean, the car was somewhere at those times, but it's not in this table. And then you can go further. You could say, well, what about at 0.1 seconds or 0.01 seconds and so on. And so in reality, the left-hand side here, time, would be a continuum of variables. But a continuum is like an infinity of variables, and so you can't possibly write that down. And experimentally, you can't get that either. Okay. So experimentally, you really have this kind of like discrete places, discrete number of x's and t's. Theoretically, you could fill in the gaps and get an infinity of positions, each for a given time. Okay. Now, the mathematical structure where if you have a single variable and you plug that in like time and you get one and only one value out is called a function. Okay, so we actually say that x is a function of t. Okay, what that means, this is a mathematically rigorous term, what that means is that for any given value of time, there is one and only one value of x. Okay, so you plug in a value of t and out pops a value of time. We denote that as x is a function of time. So this is actually functional notation. This is not like x times t, okay? It's x as a function of time, all right? And just to remind you about functional notation, usually in math you write like y is equal to f of x, okay, where f is the function, x is the independent variable, and y is the dependent variable. You plug in a value of x and then crunch through f, and then out comes one and only one value of y. Okay, and it's crucial that there be only one value that comes out of that, and that's what defines a function. In other words, the car is only at one place at any one given time, so therefore it's a function. All right, so but that's the way we say it in math. I'm using the same notation in physics. We use the same notation, but instead of f we use x. So x is a function of time here. Okay, so the position is a function of time. All right, now if you could construct such a function, all right, it would give you all the information about the motion, because you could, ask any kind of detail about like, where is the car now, where's the car now, and you've in theory you've got all the information. However, there are other kinematic quantities that you can derive from x that are of interest. Okay, so x is a function of time. That's usually known as the position. That answers the question, where is this object at a given time? Okay, so so the position is, where is it at a given time? How far is it from the origin at a given time? Is it to the right of the origin? Yeah, that would be x is greater than 0. Is it to the left of the origin? That's x is less than 0. So these kinds of questions about like where it is, those come out of the position. All right, and again, this position does contain all the information, but you might ask a different kind of question that isn't immediately obvious from x of t, and that is, how fast is the object going? And this is what's known as the velocity. Okay, so the velocity basically asks the question, we say, what's the velocity? That's like asking, how fast is it going at a time t? Okay, and if the velocity is positive, then it's going to the right, it's moving to the right, and if it's negative, it's going to the left. Okay, now it's not obvious how v comes from x. I'm going to show you that in a minute, but the velocity does come out of the position function. Okay, so again, x of t contains all the information in it, but you might want to ask a question about the velocity, and you can get that out of the position as a function of time, and you'll see how in just a minute. Okay, there's a third kinematic quantity that's interesting, and it's sometimes confused with the velocity, so let's go a little bit carefully here. It's the acceleration. It's not how fast is the object going, that's the velocity. It's, is it speeding up or slowing down? Okay, and so if it's speeding up, then you have a positive acceleration, and if it's slowing down or accelerating in the negative direction, then you've got a negative acceleration. So it's not the velocity, but is the velocity changing? All right, and this is known as the acceleration. And so to give you some clear examples here, if you're driving down the street at 50 kilometers an hour, 30 miles an hour, 50 kilometers an hour, if you're driving and you're just constantly going at 50 kilometers an hour, that's your velocity, 50 kilometers an hour. But your acceleration is 0. Why? Because you're always going at 50 kilometers an hour. You're not speeding up, you're not slowing down, you're at 50 kilometers an hour, and so you've got no acceleration. You've got a velocity, but no acceleration. You're not speeding up or slowing down. You're traveling at constant velocity. There's no acceleration. Okay. Another example, one where there is acceleration, is you're at a stop sign. Okay. And when you're at the stop sign, what's your velocity? Well, you're not moving. So your velocity is zero. Okay. So you get zero velocity. And then you step on the gas. Well, your velocity was zero. And then it's like 10 kilometers per hour. Then you speed up to 20 kilometers an hour, then 30, 40, and finally you're up to 50 kilometers an hour. See how you were speeding up? Your velocity wasn't constant. It didn't stay at 50 all the time. It started at zero and it built up to 50. Okay. And so when your velocity changes over time, then you have an acceleration. Okay. So again, these things get a little bit confused, and you might be confused even right now, but a lot of these things, try to understand them just a little bit at the beginning, and then as you start to see more and more, especially with the problems, the concepts become a lot clearer. Okay. And so the acceleration also can be derived from the position. Okay. And so how does that work? How do you get the acceleration? Like, what is the relationship between the position, velocity, and acceleration? Okay. All the acceleration and velocity can be derived out of x. How do you do that? All right. So before jumping in and just throwing the formulas at you, I need to give you a little bit more intuition. And the intuition here is the difference between what's called an average and an instantaneous. So in the case that I'll start off with is an average and instantaneous velocity. There's also an equivalent of an average and instantaneous acceleration. Okay, so what do we mean by an average velocity? All right, so it's basically the velocity over some finite interval of time. So what do we mean when we say velocity? That is, how fast are you going? What kind of question are you asking? And it's pretty intuitive. Suppose that I'm driving from Buffalo to Niagara Falls, New York. Okay, and Niagara Falls, New York is about 30 miles away, and I'm driving at 60 miles an hour. All right, that doesn't mean I'm always driving at 60 miles an hour, but roughly speaking, you know, sometimes a little bit more, sometimes a little bit less. You might ask the question, what was my average velocity during that trip? Okay, that's not the velocity at any given time, because at any given time I might be going faster than 60 miles an hour. At another given time I might be going slower, but on average, say I'm going 60 miles an hour. Well, if you have a distance that you've traveled, this delta x is like your change in position, and that's how far you traveled. Okay, so say I traveled 30 miles. All right, and I traveled 30 miles, and how long did it take? That's your delta t on the bottom here. That's the change in time. All right, say it took 30 minutes or half an hour. 30 miles in half an hour is 60 miles per hour on average. That's the point. Because I'm doing this over a large interval, a half-hour interval, it's not how fast I'm going at one particular instant in time. It's how fast I'm going over the whole trip on average. Okay, and so once again, you know, if I travel 30 miles in half an hour and I plug that in here, I'm going to get 60 miles per hour as an average. Did I travel 60 miles an hour during the whole trip? No. Sometimes I might have been going only 55. Sometimes I might have been going 65. Sometimes I might have been going 70. Sometimes 40. You know, up and down, up and down. My instantaneous velocity might have fluctuated, but on average, given that I traveled 30 miles in half an hour, I traveled at 60 miles per hour. Okay, this is known as the average velocity. Now I introduce it here. We're actually not going to use it that much. Most of the time we're going to use this instantaneous velocity, but to get to the instantaneous velocity, I have to first define this average velocity. So what do we mean by an instantaneous velocity? All right, well, actually before that, let me just do a very quick example to really solidify the idea. Sorry, I was going to jump ahead a little bit too quickly. So as an example, using the above table, let's find the average velocity for the time interval from 0 seconds to 1 second. By the way, average velocity often has this little bar on top. If you've taken statistics, that means that it's that's the symbol for average. Okay, so if you see v without the bar on top, that just means regular velocity or instantaneous velocity. The bar on top is the average. Okay, so just to see how this works, let's say we want to calculate the average velocity in that table that example that I gave up above, from 0 seconds to 1 second. Okay, and then we want to do the average velocity from 1 second to 2 seconds, and then we want to do the average velocity from 0 seconds to 4 seconds. How would you do that? Well, here's the formula. The average velocity is equal to delta x over delta t. Okay, and what do you mean by delta? That means like a change in position. So the distance you traveled is the change in position. It isn't x, because that's where you are. It's how far you traveled along x. So you have to subtract the initial from that, okay? And so your delta x you can write as the position at 1 second and minus the position at 0 seconds, okay? So that's basically how far you traveled between 0 and 1 seconds, okay? So x at 1 second minus x at 0 seconds. The delta t, well, if you're going from 0 to 1 second, what's that time interval? 1 second. So it's 1 minus 0 on the bottom here, okay? Now, if you look at the table, I won't scroll up, but if you look at the table, at 0 seconds, the car was at 1.6 meters from the tree. And at 1 second, the car was at 3 meters from the tree. So the delta x is going to be 3 minus 1.6, okay? Divided by the delta t, which is 1. And you get that on average, during that first second, from 0 to 1 seconds, the car was traveling at 1.4 meters per second, okay? So there you go. Now, I have here the units. As I introduce formulas in the course, and physical quantities that are based on those formulas, I'm going to show you what their units are, okay, the MKS units, okay? So this symbol here, we have these square brackets around a variable like the velocity. Basically, the square brackets ask the question, what are the units of? So what are the units of the average velocity? Well, the units of average velocity are the units of the change in position divided by the time interval, delta t, the units of delta x divided by delta t, okay? And so here, what are the units of delta x? Well, the units of delta x are meters, because even though you're subtracting meter from meter, when you subtract meter from meter, your answer is in meters. And your delta t, that's your time interval, and that's in seconds. And so the MKS units for velocity are meters per second, okay? And here I just note that, again, the symbol of the square brackets around some quantity is asking what are the units of. All right, let's do another example very quickly. This is pretty easy stuff. In part B, I said, what is the average velocity between 1 second and 2 seconds? Okay, if you scroll up, you'll see that that's what I'm asking. So now my delta x is, what is the position at 1 second? What is the position at 2 seconds? Subtract the two. The position at time t equals 2 seconds minus the position at time equals 1 second. And that tells you how far it traveled in the time interval from 1 second to 2 seconds. And if you look at the table, that's 4 minus 3. Okay. And then the delta t on the bottom, well, the interval started at 1 second and ended at 2 seconds. So the time increased by, the delta t is 1 second. 2 minus 1 is 1. And so when you work that out, it turns out to be 1 meter per second. So the average velocity during the time interval from 1 to 2 seconds is 1 meter per second, okay? So you'll notice that, if I scroll up here, during the first second interval, that's from 0 to 1 seconds, it was traveling with an average velocity of 1.4 meters per second. But then during the second, that is the time interval from 1 to 2 seconds, it actually slowed down a bit, okay, on average, down to 1 meter per second, okay? And then just to, drive the point home, what's the average velocity during the entire trip? Well, the entire trip starts at 0 seconds and it ends at 4 seconds. Again, if you look at the table above, you'll see I have a few entries, but the very first entry was at 0 seconds. The very last entry was at 4 seconds. And so the change in position, that's how far it traveled in 4 seconds, was the position at 4 seconds minus the position at 0 seconds. And looking at the table, at 4 seconds, it's at position 1 meter, and at 0 seconds it's at position 1.6 meters. So it actually slightly moved in the negative direction over the entire trip, okay? Which makes sense because, it starts at 1.6 meters and it actually ends up at 1 meter. So it actually moved to the left, which is in the negative direction, all right? So over here you'll see that delta x is 1 minus 1.6. Delta t, now this is the delta t for the entire time interval. So this is starting at 0 to 4, which is 4 seconds, 4 minus 0. And if you work that out, you'll see that actually it has a slightly negative velocity during the entire trip, average velocity. So even though it moved to the right for a large portion of the time, it stopped, turned around, and went the other way, so that overall on average, it was actually traveling in the negative direction, okay? So that's your story with the average velocities. I do want to say something about the negative signs, and so I'm going to go back to that diagram. I have it noted here, okay, what the negative signs mean. But let me just show you very clearly what negative signs mean and positive signs in this diagram right here. So we're way back up here at the top And let's look at this diagram again. The sine is basically the direction. In 1D, there are only two possible directions, to the right or to the left. In 2D, it's much more interesting because there's an infinity of possible directions. But in 1D, we're either on the right or to the left, okay? Now, when the sign is positive for x, that is the position, it means you're to the right of the tree. If x is negative, that means you're to the left of the tree, okay? Now, if your velocity is positive, it means you're moving to the right. Even if you're on the left side of the tree, which means, x could be negative, the velocity could still be positive because you could be on the left side of the tree, but moving in the positive direction. So a positive velocity means you're moving in the positive direction, okay? A negative velocity, again, it doesn't matter which side of the tree you're on. A negative velocity means that you're traveling in the negative direction. All right, so that's how you interpret those signs. So both x and v can be positive or negative, and the interpretation for x is where are you? So you're either to the right, positive, or to the left, negative of the tree. And for the velocity, it's what direction are you moving into? Because velocity is, a motion. And so if it's positive, you're moving to the right, and if it's negative, you're moving to the left, okay? And I'll get to the acceleration, which is a little bit more subtle later, but let's move back to where we were in our notes here. Okay, and so we had done some examples with our average velocity. Again, average velocities they're kind of interesting, but they're not what we're mostly going to be working with. We're mostly going to be working with instantaneous velocities. So I introduce it first because you can't really understand instantaneous velocity unless you understand your average velocity first. So what is an instantaneous velocity? Well, as the name suggests, it's a velocity at an instant in time. But how would you get such a thing? How do you get a velocity at an instant of time? A velocity over an interval of time makes sense because you just say, well, over that 1 second or 4 seconds or whatever it is, it traveled this far in 4 seconds. So you take the distance it traveled divided by the 4 seconds, and that gives you the average velocity. But an instant is infinitesimally small. So how do you divide by 0? Well, you don't. And if you think calculus is coming up, you're right, because that's exactly where the calculus comes in. If you take that delta t in the formula above, delta x divided by delta t, and you make that delta t smaller and smaller and smaller, eventually you're going to make it so small that it becomes an infinitesimal, okay? This is the limit, okay? So basically, the limit in which delta t becomes infinitesimally small, approaches 0, in the previous formula, that's how you get your instantaneous velocity, okay? Now, that's mathematical and it's theoretical, all right? Remember that experimentally, you can't make your delta t infinitely small. Why? Because your clocks don't measure it infinitely small, okay? So, most stopwatches will do at least a second, but, I've got a stopwatch on my phone. You probably have one on your phone too. You'll see a lot of them do tenths of a second or even hundredths of a second, okay? But even a hundredth of a second isn't infinitely small. What about a thousandth of a second? What about a millionth of a second, a billionth of a second? You might ask the question, how small do I have to make delta t before it becomes an instantaneous velocity? Well, mathematically, in the limit, this quantity, delta x over delta t, becomes a derivative. And so there's a mathematical way of actually doing this with delta t becoming infinitely small, okay? But experimentally, it's not that rigorous. You don't have to be that extreme. As long as your delta t is at the limit of your instrument, that's it. You're basically at the instantaneous velocity. So you get an instantaneous velocity when you're driving your car. When you look at your speedometer on your car, that's giving you an instantaneous velocity. It's not really doing calculus when it does that. It does actually does do an average velocity, but over a really, really small delta t, so small that you don't care. You don't care. It's good enough, okay? If you get pulled over by a police officer, you're not going to be able to use the excuse that your speedometer doesn't have a small enough delta t in calculating the instantaneous velocity. That's not going to work. It's small enough, okay? And so experimentally, there is such a thing as small enough. Theoretically, that is, mathematically, we can actually make it infinitesimally small, and in the limit, the delta x over delta t turns into a derivative, as we'll see in a second, okay? But I just wanted to make that connection because, people naturally will ask if the instantaneous velocity is calculated using the same formula as the average velocity just with a small delta t. How small do I have to make delta t before I become instantaneous? And that has two answers. Experimentally, it's when you hit the limit of your instrument. Theoretically, you can make it infinitely small because mathematics allows for that, and that's your calculus. Okay. All right. So let's take a look at that formula. So here, this is now the rigorous definition of instantaneous velocity. You'll see I have v, but I've taken off the bar on top because it's not an average velocity. Okay. And this is in the limit that delta t goes to 0 of delta x over delta t. So it is, the distance traveled divided by the time it takes to travel that distance, but only where delta t is really, really small. Okay. Now, just like we did a minute ago, when we wrote delta x, we can write it as delta x, x of time. X is a function of time. Here you would have the initial would be x of t, and then a little bit later, delta t later, you'd have x at t plus delta t. Okay, so this is where it is at time t, and this is where it is at time t plus delta t, just a little bit of a delta t later, divided by delta t there. If you take the limit of this goes to 0, this, by definition, is the derivative. Okay, it's the derivative. Okay, so why did we do this? Why did we go here? Well, remember that velocity was one of the things, instantaneous velocity is one of the things that we want to be able to get out of our position function. Okay, so experimentally or theoretically, we have an x of t, a position function. And we ask this question about the velocity. And you say, well, I've got a position function. How do I get the velocity out of a position function? Here's the answer. You take your position function, you differentiate it with respect to time, and you get your velocity. Okay, now I'm going to unpack this because you guys kind of know what a derivative is. It's probably a little vague in your head, but you kind of know what it is. But let's really unpack this so we have a very good intuition in what's going on. And probably the best way to do that is to do it with pictures. And I'm sorry here, I'm kind of my image here is kind of covering the word slope here, but this straight line here, this straight line is just is exactly that. It's a straight line. The curved line here, the curved line, you can see I've labeled that line x of t. That is where the object is. I got to move it up just a bit more. Okay, that's this curved line right in here. That curved line is where the object is as a function of t. Okay, so this is the position as a function of t. And down here along the independent variable, that's our time, and the dependent variable is the vertical axis. Now I know you guys in math usually put the x down here and you put y up there, but we've kind of changed the names a bit because the independent variable goes along the horizontal axis. In our case, that's time. Okay, and the dependent variable, that's the thing that comes out of the function, the value that comes out of the function, that's the position that goes along the vertical axis. So that's why time is along the horizontal and x is along the vertical. And the curved line that you see here, that is x is a function of time. Okay, so here's time t, and here's time t plus delta t. So here's the initial time, and there's the time at delta t later. Okay, and over here, this is the position at time t, and here's the position at a later time. Okay, so the position at a later time you can say is x plus a little bit extra, a little delta x. So they're like that. Okay, now if you look at this and you say, okay, well, I want to go from that point there to that point there. If you calculate delta x is what? Delta x is the rise. Okay, and if you want to calculate delta t is the run. And if you do delta x divided by delta t, you get the slope. You actually get the slope of this straight line here. Okay, so I just moved it down so you can see my label there. So you get the slope of the straight line. All right. Now I think you can agree that that straight line doesn't really, it kind of approximates, but it's not exactly the curved line here. But it's kind of approximating it. All right. And so if all you've got is an average velocity, then the slope here is a little bit indicative of the velocity during the interval from t to t plus delta t. Okay, but it isn't exact. All right, now here's the thing, so this is the diagram for average velocity. All right. Again, average velocity is your delta x over delta t, where delta t is finite. Here, delta t is finite. Okay, it's not infinite, and then you shrink it down to nothing. It's got some width to it. Okay, so this delta t here, that's the run, and this delta x here is the rise. If you take the rise divided by the run, you get the slope. So already you're getting an indication that the slope of an x versus t graph is the velocity. But what happens if you start to make that delta t smaller and smaller and smaller? Well, as the delta t becomes smaller and smaller and smaller, eventually, you know what, I'm going to move my image down here. There we go. And yeah, okay, I think you can see that. Let me just move that down a little bit. All right, so we still have the time axis down here. As I make my delta t smaller and smaller and smaller, you say, where did it go? Well, it got so small that it squished right up to the original time, okay? And the delta x, you say, where did that go? Well, it got squished right up to x there, like that. And so here's x at a particular time. Here's the function. X is a function of time. And now when you squeeze that down, what you get is this tangent line, and the tangent line touches it right at that point there, okay? So that's the slope of the previous diagram, which was a line between 2 points, got squished down to a tangent line, okay? The slope of the tangent line at a particular point in time of an x versus t graph, that's your velocity. Okay, let me say that again. The slope of this tangent line of an x versus t graph, that's the velocity at that particular time, okay? That's also the graphical interpretation of the slope, okay? So let me do this one more time. We'll go over here. This is the diagram for your average velocity. So you have 2 points, and you just want the slope between those 2 points. It's an approximation to the slope of the line, but the line is curved, so it's not exactly it. But as these 2 points start to get closer and closer together, the line doesn't just cross it at 2 points, it crosses it at one and only 1 point. And so the 2 points coalesce into 1 point, and you get a tangent line like that. And the slope of the tangent line is the derivative, okay? So this is just another way, this is a graphical way of showing you what the relationship is between the velocity and the relationship between the velocity and the position. If you have the position as a function of time, the derivative of that is the velocity, or speaking graphically, the slope of the tangent line at a particular point, that's the velocity. Okay, so we'll look at some problems with that in a minute. And before we do, let me just show you that, or argue that it's equivalent with acceleration, not in as much detail, but before we jump into some problems. But let's look at acceleration. So acceleration also has an average and instantaneous, and they're defined very much synonymously to the way average and instantaneous velocities are defined. Okay, so how does that work? Well, here, this is the average velocity. You see the line on top indicating that it's an average velocity. Average acceleration. Okay, so the line on top of the A is that this is an average acceleration. So what is acceleration? What do we mean by that word? It means the change in velocity, or the rate at which the velocity changes. So just like with velocity, we had delta x over delta t, here with acceleration, we have delta v over delta t, okay? If we're talking an average acceleration over some time interval, well then you're going to take delta v, the change in velocity over that time interval, divided by the delta t, the time it took to make that change, okay? However, if we want the instantaneous velocity, you do the same thing as you did above. Sorry, I said instantaneous velocity again. I meant instantaneous acceleration. To get the instantaneous acceleration, you do the same thing you did above with the velocity. You take the limit as delta t goes to 0 of delta v over delta t, and it just turns out to be the derivative, like that, okay? Now, a is the first derivative of the velocity with respect to time, but the velocity is the first derivative of x with respect to time. So another way to think of the acceleration is that it is the second derivative of the position with respect to time, okay? So there's a couple of ways you can get the acceleration as a function of time. If you start with the position function and you differentiate it twice, you get the acceleration. Conversely, if you have the velocity function and you differentiate it once, you get the acceleration. Okay. Now, graphically, the interpretation of the first derivative is the slope. The graphical interpretation of the second derivative is the curvature. Okay, and what that is it's not what the graph is sloping at, but how much is starting the curve as you go from one position to another point. All right, and we'll look at some graphs of that later, but let me just show you what the units are of the velocity, instantaneous velocity. It's no different than average velocity, as you might imagine, just because dx is an infinitesimally small change in x doesn't mean it has different units. It still has units of meters, and the delta t shrinks down to dt. It still has the units of seconds, and so the units of velocity, instantaneous velocity, are meters per second. The units of instantaneous acceleration are going to be the units of velocity divided by the units of time. The units of velocity are meters per second. The units of time are second, and so we have meters per second divided by seconds, and so you get 2 seconds in the denominator, and so the units of acceleration are meters per second squared. Okay, and even though I did the analysis here for instantaneous acceleration, it's the same for average acceleration. So to summarize, velocity has units meters per second, acceleration has units meters per second squared. Okay. Now, before I jump in and start doing some problems with this, you're probably a little bit rusty with your differentiation. I'm not going to throw very difficult functions at you to differentiate, okay? They're going to be pretty straightforward, and it's mostly the conceptual scheme work that I need you to remember rather than having to remember a lot of complicated calculus rules for differentiation. But you will need a few, and so I'm going to refresh your memory. And so before we jump into our first problem, let's take a look at how you differentiate something that looks like this. And again, usually in a calculus class you would use x, but here we're going to use t as our independent variable. So suppose you have a function which looks like a, where a is just some constant. And then you have t to some exponent n, and you say, I want the derivative of that. That's what this says. D by dt says differentiate all this stuff in brackets. Well, the first thing is that constants that are coefficients of some other function that you're differentiating, those constants, they just come right in front. So you can see here I have a, and my first step, I could just move the a right in front. So the derivative, the derivative operator doesn't affect the a at all. Okay, so the a just comes out in front. So now we're just looking to differentiate t to the exponent n like that. And without giving you why this works, and if you want to know why, you can either look it up or just look in your old calculus textbook. The derivative of t to the exponent n is n times t to the n minus 1. So the exponent decreases by 1, and you get an extra coefficient n out in front like that. Okay, so that's one type of derivative that we're going to be seeing quite a lot. Not so much in the near future, but a few lectures from now, we're also going to have to differentiate sine and cosine functions. So I might as well give them to you right now, okay, as reference. And you should know that the derivative of the sine function, so if you have sine of t, okay, the derivative of that is cosine of t. All right, and the derivative of the cosine function is minus the sine function. Okay, so they're not too hard to remember. All right, you're going to need one more calculus rule, and that's the chain rule. All right, and the chain rule, I'll explain it again when we get there, when we need it. But the chain rule basically says something like this. Suppose you have a function, and this is a function of just t, but it's a function of a times t, like that. Okay, so basically a is just a constant. I could have made capital A there, but I wrote little a, but a, just think of the a as a constant. And you say, how do I differentiate this with respect to t? Well, the way you do it is you first differentiate the function with respect to the whole argument. So you go df by dat, that is the whole argument, and then you differentiate the argument with respect to t. And so what you're going to get is the derivative of f, the little dash there, I probably shouldn't have used that notation here, not to mix too many notations, but the little dash just means the first derivative. So you get the first derivative of f multiplied by the derivative of at with respect to t, and that's just the a like that. All right. So if this is a bit confusing to you, don't worry. I'll rehash it when the time comes. When we get to simple harmonic oscillator, we're going to need this. Okay. But basically, this is the chain rule, and it says to differentiate with respect to this function with a complicated argument. First, you differentiate with respect to the whole argument, and then you differentiate the argument with respect to the variable of interest, which is t in our case. Okay. So there they are for reference, and at this point, we can do some problems, all right? And so let's start looking at some problems here. So let's say we have a car, and it speeds up from 50 kilometers an hour to 100 kilometers an hour in 10 seconds. What is the average acceleration? Okay, so remember what acceleration is. I have to stress this because acceleration and velocity are often confused. And earlier you could see that, I usually, even in my own mind, I sometimes will say velocity because I'm slightly dyslexic. I'll sometimes say velocity and acceleration because they are quite similar, and so they're easy to confuse. But let's be careful and be very clear here. The velocity is just how fast you're going. The acceleration is how much you're speeding up or how much you're slowing down. Okay, so if you're not speeding up or slowing down, there is no acceleration. Are you speeding up or slowing down in this problem? Well, you started at 50 kilometers per hour and you ended up at 100 kilometers per hour. So you're speeding up. So yes, there is an acceleration. Okay, how much is it? Well, you need another piece of information, and that is how long did it take to speed up from 50 to 100 kilometers per hour? And it took 10 seconds. Okay, so this car goes from 50 to 100 kilometers per hour in 10 seconds. What is the average acceleration? It has to be average. Why? Because your delta t is not infinitesimally small. It's 10 seconds. It's a finite amount. Okay. So the first thing is, even though I didn't explicitly say it here, let's convert to MKS. Okay. Like on a test, I'd be very careful about what I want as an answer. But we're doing this together, so let's get our answer in MKS. So the first thing you notice is that your units here are not MKS. Your length units are kilometers, and we need meters, and your time units are hours, and we need seconds. And we actually did this conversion in the previous lecture. So we have like our initial velocity, so I call that v of 0, so v at t equals 0 seconds. Velocity, read this as velocity at time t equals 0. That's 50 kilometers per hour. Okay. To get rid of the kilometers, multiply by 1,000 meters divided by 1 kilometer. There's that fraction which is equal to 1. It'll remove kilometers and it'll introduce meters, and then multiply by 1 hour divided by 3,600 seconds. That'll remove the hours and introduce seconds. And if you multiply this all out, you're going to get 13.9 meters per second. Okay, we actually did this example in the previous lecture, as I said, and you have to do the same thing for the 100 kilometers per hour. So this is the velocity at t equals 10 seconds because we're 10 seconds later now. Okay, so v at 10 seconds is 100 kilometers per hour. Multiply by this fraction to convert to meters, multiply by this fraction to convert to hours, and you multiply this all out and you're going to get 27.8 meters per second. Okay, so there's your initial velocity, 13.9 meters per second, and your final velocity is 27.8 meters per second. And now we're ready to calculate our average acceleration. So A with a little bar on top, average acceleration, that's your delta V divided by delta T. So what's your delta V? That's like your final velocity minus your initial velocity. The velocity after 10 seconds is 27.8 meters per second. Your velocity initially was 13.9, subtracted 2. Notice that in the middle of the formulas, I don't put in units. I only put the units in at the end. Why? Why can I do that? Because I'm guaranteed that if everything I plug in here is MKS, the units will come out in MKS. Okay. So again, initial velocity 27.8. Final velocity 27.8 minus initial velocity 13.9 divided by the time interval, 10 minus 0 seconds, and that's going to give you an average acceleration of 1.39 meters per second squared. Okay, and I just to show you that it doesn't matter whether you have a dV or a dt here, the units again are going to be meters per second squared. All right, okay, great. Now let's do a more interesting problem. That one was with average velocity and no calculus in it at all. Okay, so let's do a more interesting problem. This one, it requires some differentiation. So I'm going to give you a position versus time. Okay, so here it is. Here's a position as a function of time. All right. Now you might say, where did you get this formula? Well, I don't know. Maybe I did an experiment and the computer did a fit to the data points, and this is what comes out of the computer. Okay, and so now I can ask a series of questions. All right, well, let's look at the formula first before I do it. So this is x as a function of time, and there's a t cubed in there minus 2t squared plus 3t plus 1. Okay, so there you go. So I plug in t here. Notice on the right hand side it's all time. Okay, and then on the left hand side there's your position. Okay, so now we can ask a whole bunch of questions about this. Because why? Because that equation should have all of the information we can possibly ask about the kinematics. Questions about position, questions about velocity, questions about acceleration at all times. Okay, so let's do it. So there's a whole bunch here. Let me just read them off to you very quickly. What is the position at t equals 0? What is the position at t equals 1 second? What is the velocity at any time? What is the velocity at t equals 0 seconds? What is the velocity at t equals 1 second? And then what is the acceleration at any time? When I say any time, I want the functional form of the acceleration. What is the acceleration at t equals 0? What is the acceleration at t equals 1? Okay, so all of these different questions should be derivable from this one formula. Okay, so how do we do it? Well, let's start off. First, I want the position at t equals 0 seconds. So no need to differentiate yet. You know, you have the position function x of t. So just plug in t equals 0. So instead of t there, now I have a 0. So wherever I had a 0 on the right hand side, wherever I had a t on the right hand side, I'm going to put in a 0. So I had a t cubed, so now I have 0 cubed minus 2 times 0 squared plus 3 times 0 plus 1. By the way, the dots, those big dots like that, that's how I do multiplication, because otherwise if you put an x there, you're not sure, is that the variable x or are you multiplying? So, you know, sometimes in some math textbooks we put little dots like that. So this is 0 cubed minus 2 times 0 squared plus 3 times 0 plus 1. Well, that's pretty obviously just 1 meter. So what does that say? At t equals 0 seconds, the object is at 1 meter. Okay, that's 1 meter from some reference point, okay, from the origin. All right, and then the second question, question B, part B, is where is this thing at t equals 1 second? So same thing, but now instead of substituting t with 0 like we did here, we're going to substitute t with 1. So x of 1, okay, so 1 cubed minus 2 times 1 squared plus 3 times 1 plus 1, that's 3 meters. Okay, so at 0 seconds it's at 1 meter. At 1 second, it's at 3 meters. So you can see that it moved to the right a little bit. Okay, and then part C was, what's the velocity at any time? In other words, I want some functional form. I want v of t. And what's the relationship between v of t and x of t? To get v of t out of x of t, you differentiate. It's the first derivative. Okay, and so there we go. So v, the instantaneous velocity, is dx by dt. It's the first derivative. Now, how do you get that first derivative? Well, let's go back up here. First, remember how this works, okay? Remember how this works. So if you have some coefficient, t to the nth power, and you take the derivative of that, you're going to get that coefficient that just stays out in front. The power up here, n, that just comes out in front as part of a new coefficient. And then the n here decreases by 1. Okay, so keep that in mind, that rule there, and let's take a look at the function that we're differentiating. Here's the function that we're differentiating. Take a look at the first term here, t cubed. So what's the coefficient? Well, 1. Okay, there's like that, capital A is like 1, and the n is like 3. So this is going to, the derivative of this is going to have the 3 come out in front, and then that 3 is going to decrease by 1. So this is going to become 3t squared. And you could see here, if I scroll down, like right there, the first term, that's the t cubed, becomes 3t squared. And there it is. Okay, now what about the second term? Well, let's scroll back up to here. The second term was minus 2t squared. That minus 2, that's the coefficient, including the sign. That's the coefficient. That's that minus 2. That's like that capital A. It just sits out there in front. And then that 2 also comes in front. And then the 2 on the exponent becomes 1. Okay, and so negative 2 from the coefficient, 2 from the old exponent, 2 times 2 is 4. So this thing, when you differentiate, it becomes minus 4t. Okay, and then down here, you could see that, sure enough, there's minus 4t. And then the next term was 3t, but when you differentiate 3t, you just get 3. The t becomes 1. Okay, and what about the plus 1? Well, the derivative of a constant by itself is 0. Okay, so that plus 1 just became a 0 there like that. So there you go. There's the that function x of t differentiated with respect to time gives you the velocity as a function of time. And now we can answer the question, what is the velocity at t equals 0 seconds? Well, what do? You just take this, and wherever you have a t, you replace 0. So you have 3 times 0 squared minus 4 times 0 plus 3, and that's just 3 meters per second. Okay, so at t equals 0 seconds, this object is moving at 3 meters per second. How fast is it moving at 1 second? Well, just plug in 1 there. So v of 1, so it's 3 times 1 squared minus 4 times 1 plus 3. All right, and that gives you 2 meters per second. So it slowed down a bit. It started off moving to the right at 3 meters per second, and it slowed down, still moving to the right, but now at 2 meters per second. Okay, so it's actually slowing down. And then the next question was, what is the acceleration at any given time? So guess what? You take, let me scroll down up a bit here like that. See, yeah, there you go. You just take this function here, which is the velocity as a function of time, differentiate it again, and you get the acceleration as a function of time. Okay, so here you have 3t squared. The 3 is a coefficient that goes in front. The 2 also becomes part of the new coefficient, so you have 3 times 2, there's your 6. And then the 2 gets decreased by 1, there's your exponent of 1 right there. Okay, so the derivative of 3t squared is 6t. The derivative of minus 4t, that's just minus 4. And when you differentiate a constant here, that's 0. Okay, so the derivative of that is that right there. Okay, so the instantaneous acceleration, dv by dt, is 6t minus 4. There you go. Okay, now we can say what's the acceleration at t equals 0 seconds, what's the acceleration at t equals 1 second. At 0 seconds, you just put in 0 there, and so 6 times 0 is 0 minus 4, and so it starts off with an acceleration of minus 4 meters per second squared. And then if you put in a 1 there, the acceleration at 1 second is 2 meters per second squared. Okay, now the last thing I'm going to talk about is, what does a positive and negative acceleration mean? This is by far the most subtle thing there is. Okay, so hopefully you've got that, you understand that problem. We'll like in the quizzes, I'll give you some more of these, and you can use this one as this example as a reference. Okay, they're pretty easy in terms of actually the mechanics of them, but make sure you have a good understanding of what the relationship is between the position, velocity, and acceleration function. Okay, let's get back to this business of the sine and the acceleration. We already did that for position and velocity, but what about the acceleration? What does the sign for the acceleration mean? Like you could see here that it started off with a negative acceleration and then it became a positive acceleration. How do we understand that? Well, let's scroll all the way back up here to the top picture. So just to remind you, position, positive and negative. Positive position, you're to the right of the origin. Negative, you're to the left. Okay, positive velocity, you're moving to the right. Negative velocity, you're moving to the left. What about your acceleration? Well, okay, let's assume that you're moving to the let's assume that you're moving to the right, so your velocity is positive. If you're moving to the right and your velocity is positive, suppose that your acceleration is also positive. So not only do you have a positive velocity, but you also have a positive acceleration. What does that mean? It means you're moving to the right, but because your acceleration is positive, your velocity is actually increasing to the right. So I'll try to demonstrate this with my cursor here. You can see my cursor near the origin here. It starts off moving to the right slowly and then faster and then faster and faster and faster and faster. Okay, so it's moving to the right because the velocity is positive, but it's speeding up to the right because the acceleration is positive. What if you're moving to the right but the acceleration is negative? So if you're moving to the right like that, that's a positive velocity. Okay, if you're moving to the right and the acceleration is negative, that means that your velocity is slowing down. It's like your velocity is changing in the negative direction. So in this case, this is positive velocity, negative acceleration. You're moving fast at first and then you slow down, slow down, slow down. Stop, and then you would even turn around and start going back the other way, accelerating the other way. And the reason is that the change in the velocity is towards the left. You might be moving to the right, but the change in velocity is towards the left. Okay, that's pretty subtle. I agree. Okay, so it's a bit of a brain twister. So you have to think about it. And let me just say it again. So if both velocity and acceleration are positive, then you're moving to the right, but you're also speeding up to the right. So you start off slow and then you go faster, 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 faster to the right. Okay, if you are moving to the right, velocity is positive, but the acceleration is negative, you're moving to the right, but you're slowing down because your velocity is changing towards the left. So you might start off fast, slow down, slow down, slow down. You might even stop and then go this way like that and then swing around the other way. Okay, now we'll see this again. Okay, when I do problems where I throw things up into the air, you'll see that the acceleration is always downwards, but sometimes the velocity is up, sometimes the velocity is down. That'll definitely help. Okay, but I admit that this is kind of a subtle idea. You have to think of the acceleration as the change in the velocity. So it's not so much which way is it moving, but which way is the changing the velocity, and what direction is the changing the velocity in. So, if the acceleration is positive, it means it's speeding the velocity up to the right. And if it's negative, it means it's speeding up to the left. You could be moving the opposite direction to your acceleration, in which case the acceleration would decrease the velocity first, even get it to zero, and then turn it around and have it going the other way. Okay, this is the end of the first lecture. It's just an introduction to kinematics. We have a lot more to do in 1D kinematics with respect to particular motions. That is motion where the acceleration is constant, and motion where the acceleration is sinusoidal. That is where it bobs back and forth, and that's what the next two lectures are about. Okay, thank you.